Hello everyone, welcome to another exciting week of stats and stuff. This is week 5 lecture 1 on 2 sample t-tests. So let's see, when do you use 2 sample t-tests? This is going to be a shocker. You use them when you have 2 samples. So you want to compare the sample, the mean of one sample to the mean of another sample. So note that there's a little x bar 1 and x bar 2. That means mean of sample 1, mean of sample 2. So usually the IB is nominal with 2 groups. Can be ordinal, but usually it's nominal. The DV is something that's going to be interval or ratio, so something you can take means of and have them be meaningful. So here's the catch. There's 2 different types of 2 sample t-tests. So there's two sample t-tests. One is called the independent samples t-test, and it's basically the t-test when you've got a between groups design. Then there's the Paired-Samplest t-test, and it's the t-test when you've got a within groups designs or repeated measures or whatever, pre-post. So normally you only run one or the other when you're testing your hypotheses, right? Because you either have a between or within group design. So I just want to point out in this week's assignment, you run them both, but it's just so you didn't have to, load totally different data. But normally you wouldn't do that. So how do you write hypotheses when you've got means? Well, there is more than one way to do so, just like for everything, depending on whether you've got one or two-tailed tests, and then depending on what your prediction of direction is. So non-directional or two-tailed hypotheses, again, just like before, you're not stating the direction of the expected results. So remember in the past it was the things will differ or these things will be related. It's the same sort of idea here, the groups will differ. So let's say you're comparing the means of 2 groups on words remembered when one group was memorizing related words and the other group unrelated words. You could write the hypothesis as follows. And again, x bar is the sample mean, where x bar 1 is related words, x bar 2 is unrelated words. So it's the average numbers of words remembered by those who are remembering related words versus unrelated words. So a hypothesis in words, a research hypothesis stating this, is something like the numbers of words remembered will differ between memorization strategies. That would be a two-tailed hypothesis. So start with your alternative. You've got the mean of group 1, the mean of group 2. I'm not saying which one of these is going to be higher or lower. I'm just saying they're not going to be equal. So it's exactly like correlation in one sample T. So then your null is where you're wrong. Where's the one case you're wrong that the words remembered will differ between memorization strategies? Well, if they don't, if they're equal. So that's your null. So you can also have directional or one-tailed hypotheses with 2 sample t-tests, and here you are stating the direction of the results. So which group you think is going to be higher, x bar 1 or x bar 2? So typically this is what we do in dissertations because you did some research and you have reason to believe that one group is going to do better or be higher or whatever it is or lower than the other group. So this is how you write one-tailed hypotheses. So 2 different ways. Start with this one. For example, let's say you hypothesize that those who memorize related words, which is x bar 1, will remember more words on average than those memorizing unrelated words, which is probably true, right? You can remember a group of colors more than just random words. But anyway, this is just a didactic exercise. Starting with your alternative, you think that the mean number of words remembered by x bar 1 is going to be bigger than x bar 2, right? So, not so shockingly, greater than. So where are you wrong? That's what goes in your null. You are wrong if the number of the mean words remembered is lower than those remembering unrelated words, or there's no difference at all. So how do you say where you'd be wrong? Well, you'd be wrong if x bar 1 is less than, or if they're equal to. That's how you write it. So you could have hypothesized the opposite. I think it's kind of goofy in this study, but theoretically, sometimes you think group 1 is going to be lower. So basically, we're just going to switch these signs on the greater than, less than signs above. So you're saying, hey, for whatever reason, those who are trying to remember unrelated words are going to remember more words on average. Well, the bigger one's going to be x bar 2, right? So less than. The mean number of words remembered by group 1 will be less than the mean number remembered by group 2. So your null, again, is just all other possibilities. There's 2 of them. That is, well, you're wrong if group 1 remembers more or if there's just no difference. So greater than or equal to. So let's do a worked example of an independent t-test. These are really common. It's probably one of the most common stats besides correlation in dissertations and other research. So let's say a researcher hypothesizes that behavior therapy will result in greater life satisfaction improvement than receiving no therapy. It's kind of reasonable, right? So you got 2 groups. Your IB is therapy condition. The first group is behavioral therapy. They're X bar 1. It's going to be their words remembered. And then no behavioral therapy or no therapy at all will be X bar 2. Your DV is life satisfaction scores. So specifically, the way they did this study is they looked at pre-post. So they measured them at baseline, and then one group got therapy and one group didn't. They measured them afterwards. And the actual DV you analyze is the change score. So how much did it change from before and after therapy? Pre-post change score. So check out how the data are set up. This is how data are set up for between groups designs and SPSS. There's one column that represents the independent variable. That is what treatment group they're in. So here it just shows therapy, but if you keep going down, it would show the no therapy folks. And then another column for their dependent variable. That is life satisfaction change. So yeah, that's it. That's the setup. 2 columns, one that's the IV, one's that's the DV. So continuing our example, how would we write our hypotheses that behavioral therapy will result in greater improvement of life satisfaction than no therapy? Well, we think X bar 1 is going to be bigger than X bar 2, right? So this is going to be a one-tailed hypothesis. So how would we write that X bar 1's average improvement in life satisfaction will be higher than that for those who got no therapy? That is X bar 2, well, greater than. Where are we wrong? Those are going to be our null. Well, we're wrong if behavior therapy results in less improvement in life satisfaction or no improvement, equal, right? So these are the actual means for the study. So this is the SPSS output you'll get. And the mean you can see was 6.1 average change. It's positive, so it's post minus pre. So they went up 6.1 points on average for those who got the therapy. They went up as well for those who got no therapy, but it's much smaller, right? 0.6667, so 2/3 of a point. So the mean change scores are consistent with this hypothesis, right? That behavioral therapy results in greater improvement than no therapy. Why is that? Well, the sort of directionally, 6.1 is a bigger improvement than 0.6667. That's why. So the question remains, is this 5.43 difference, that is, just the the therapy group score minus the no therapy group scores 5.43 difference in points. So is that just a one sort of skittle or 2 extra skittles difference in the sample, or is that a real difference? That's the question. That's why we do the stat, because we're really bad at judging that. So we're going to calculate the stat, and the stat's going to tell us if indeed that is just chance or if it's a real difference. So independent samples T, like everything else, has assumptions, and those statistical assumptions have to be met in order for the test to provide the correct, have statistical validity actually, provide the correct interpretation for the data. So the first one's independence, kind of a no-brainer. So it's for between design, which means that the folks in the different groups are unrelated, except for the fact that they're all in your study, right? So it is a between groups design. That is assumption 1. If you violate that, I mean, really it just means you should have done the other type of 2-sample t-test that we're going to talk about in a couple minutes, the paired one, right? Because you got pairing. So the second assumption is normality. We've seen this before. It's that the DV is normally distributed. It's approximately, right, normally distributed for both samples. So the way you test it is you look at the skewness statistic for each of the groups, like we did, what was it, like the first week of class, second week of class. So you want that skewness, doesn't have to be perfectly normal, it's just approximately normal. So you want skewness to be less than 2 for both groups. So it turns out that t-tests are pretty robust to just sort of normal deviations from a normality assumption. So I've discovered over the time that people don't know what I mean when I say robust. So what's robust mean? Yes. So the results you get from t-tests are pretty accurate, even if the assumption is violated. So it is an assumption, and it does mess up your results somewhat. But for the most part, because it's robust to deviations, it doesn't cause that many problems, particularly if two things are true. Sample sizes are large, so sample size of group 1 plus the sample size of group 2 is 50 or more, so there's probably 25 in each group. And the sample sizes are equal. Those two things are true. Sort of normal deviations from normality are not that big of a deal. However, it is a big deal for this last assumption. So the last assumption is called the homogeneity of variances. And this says, so the prior one said that the scores for each of the group, in this case, like this example, we're looking at life satisfaction scores, change scores, right? It's approximately normally distributed for those who got the therapy and approximately normally distributed for those who did not. This assumption is slightly different. It's about the spread. It says that the DV has approximately the same variability, that is spread, for sample 1 as sample 2. So each group has about the same variance, hence homogeneity of variances. So on the bottom, you can see there's two distributions. Not only are they normal, but they have the same variance, exactly the same, 5 and 5. On the right, you can see the sample on the left has much less variance, so it's much tighter. The scores are much tighter together. On the right, they're more spread out. So you got a variance of 4 versus a variance of 9. That would be heterogeneous variances. The left would be consistent with this assumption. The distributions on the right would be inconsistent with this assumption, indicating a violation. So two-sample t-tests, in fact, all the t-tests are not robust to violations of this assumption, meaning if you violate this assumption, it really messes up the results. What happens specifically is that the type 1 error rate is higher than what you state as your alpha level. And we call that type 1 error inflation. So if you violate the assumption, you think it's alpha of 0.05, you got a 5% chance of making a type 1 error rate, but in reality, you've got something higher than 5%. How much higher? Yeah, that's what pure statistics people do for a living. I don't know. You just know the general direction of things. Is it biases things that you're more likely to make a type 1 error? And that's particularly true if the sample sizes of the two groups are unequal. So, one's 30 and one's 20, it's even worse. So this is actually tested as part of the SPSS output. It outputs something called Levine's test for equality of variances. And you look at this test and make a decision about which stat line for the independent sample T you're going to interpret. There's two lines that are going to be printed. So if the homogeneity assumption is violated, you will use the equal variances not assumed results. Okay, so SPSS automatically spits this out, and it's an alternate version of independent samples t-test that does not require this assumption. It's less powerful though. That's why it's not, why wouldn't you just use this always? Well, it's because it's less powerful. If it's truly like severely violated, the other thing you can do is not use an independent samples t-test at all, but use the weed whacker backup equivalent of it, which is the Mann-Whitney U test. So if you look above it in the matrix of statistical tests, you'll see that Mann-Whitney U is the equivalent of independent samples t-test for ordinal data, and you can use that test in cases where the assumption is severely violated. All right, back to our examples. Let's actually look at how we test the homogeneity assumption using SPSS. So Levine's test for equality of variances. You first look at this test again to determine which line of independent sample t-test results to interpret for the actual t-test. So it's like a road sign. That's the way I think of it. It tells you turn left or turn right. And it's really keep going on one line or drop a line is what it tells you. So this is what it looks like in SPSS, and it's the first thing that pops up in the row. Equal variance is assumed, equal variance is not assumed, and you get this, it's an F value. But most importantly, there's the sig value. So if Levine's sig is greater than 0.05, the homogeneity variance assumption is not violated. You've met that assumption. You will use the equal variance is assumed line. So see that row in there? Equal variance is assumed. You just keep going across the line. I truncated it after the sig value, but you just keep going across the line. You're good to go. That's if sig for Levine's is greater than 0.05. What happens if that sig is less than 0.05? Well, you violated the homogeneity variances assumption. And so what you want to do is drop a line and read the equal variances not assumed line of the t-test results. So it's not that big of a deal, right? It's just a road sign that says keep going. If it's greater than 0.05, you just keep going. If it's less than 0.05, drop a line and keep going. So not too bad. So here we've got a sig for our Levine's of 0.109. So which line of results are we going to read? Well, because 0.109 is greater than 0.05, we have met the assumption of homogeneity variances, and we're just going to go ahead and read the equal variances assumed t-test results. So when and if you run into where that sig value is less than 0.05, it's not that big of a deal. You just drop a line on the output, and you're going to read across this line that's equal variances not assumed. So it's not that big of a deal. It's violated so frequently, they actually built in like a backup test right into the output. So let's actually go ahead and interpret our t-test now. Our decision rule, this is kind of the decision rule for everything moving forward, by the way, is if sig is greater than 0.05, you retain your null, right? So regardless of whether it's a one-tailed or two-tailed hypothesis, sig greater than 0.05 means those two means are not even different, okay? The difference could have happened just by chance. So stop, done, no difference. Average life satisfaction was equal between the groups, right? Type of therapy had no effect, that kind of thing. However, if your sig for your actual t, so not Levine's now, t result, is less than 0.05, you're probably going to reject your null, okay? So it does tell you that the means of the samples significantly differ from each other. They're statistically significantly different, however you want to say that. So if you got a two-tailed hypothesis, that's all you need. You reject the null just based on that. Sig less than 0.05, if you got a two-tailed hypothesis, yep, the means are different. If you have a one-tailed hypothesis, though, you got that extra rule. So you know they differ. Did they differ in the direction you predicted or was predicted by the hypothesis? So that is the second thing that must be true for you to reject if you've got a one-tailed hypothesis. Not only does sig have to be less than 0.05, the means have to differ in the direction you predicted or was predicted by the researcher. So SPSS only prints two-tailed p-values, kind of like for one sample t, so it's not hard to get a one-tailed p-value. You just divide sig by 2. That's all you got to do. So particularly when it's 0, 0, 0, it's really easy. But you just divide the sig value they give you by 2 if you have a one-tailed hypothesis to get the correct sig value. So here's the output, and notice first of all that it starts with the Levine's over there, which I had truncated in the prior slide. You can see there's 2 rows of t-test results, right? 2 different sigs out there, and they're sig two-tailed. And so we know that because sig is for Levine's was 0.109, we have equal variances. We have met that assumption, so we're just going to keep reading that first line of results like that. So they print a bunch of extra crud on here, standard error, confidence intervals. This is one of those things where you don't really need to know it, so I don't bother. Like, if you really want to know, hit me up during office hour. So based on the actual t-test results, we've got a sig value of 0.000, and that's two-tailed, and we have a one-tailed hypothesis. But 0 divided by 2 is still 0, right? So are we going to reject or retain the null hypothesis? Well, sig's less than 0.05, so the two means differ, right? The means that are being compared here, those who had behavior therapy and those who did not. It shows you the mean difference was 5.43333, just keeps going. So it's a 5.4 life satisfaction improvement difference between the groups. So who did better? Well, those who had the life satisfaction training did better. And so we are going to reject the null hypothesis. First of all, because sig's less than 0.05, and secondly, because of the therapy group, those who had the behavior therapy had higher mean life satisfaction change than the no therapy group. It was plus 5.43. So bringing it all home for grandma, you'd say, well, yes, life satisfaction, behavior therapy did improve the life satisfaction of those who received it compared to those who just got no therapy. So let's take it all the way home. Independent samples t-test. Let's do our effect size in our APA format. So our effect size is called omega squared, which we affectionately call butt squared. It tells you the proportion of variability in the DV that's accounted for by the IV. So it's very meaningful. So it can go from 0 to 100, right? 100% would be all the variability in the DV is accounted for by whether they got DV level 1 or IV level 1 or IV level 2. This is the formula for it. Everything comes from the output. So here's that same table from the last slide. We got to get our t values, and we need n of group 1 and n of group 2. That's just the sample size, how many were in each group, and it was 30 in each group. So that is it all filled out, and it comes out as 0.22. So if you turn it into a percent, it's 22%. So t value goes there, t value goes there, sample size is 30 and 30. Go in the latter spots, and you do the math, you get 0.22. To write this up in APA notation, we've got to follow their format again. It's kind of like it was for one sample t, right? We just got to fill this in. Where does all this come from? A t of 58 degrees of freedom was equal to 4.26, so you go to 2 decimals. Our p was less than 0.05, right? So we use the less than sign, and our omega squared was 0.22 from up at top. So the take home for grandma, behavior therapy resulted in greater life satisfaction improvement than no therapy, with 22% of the variability in life satisfaction change scores accounted for by the treatment group, which group they were in. So I hope that makes sense. Let's do a paired samples t-test now. So again, this is like the same thing. You got two groups and an interval or ratio DV, but you've got a design that is within groups. So same people or twins or matched people, that sort of thing. So let's say a researcher hypothesizes that behavioral therapy will result in improved life satisfaction. So we're just looking at the 30 people who got it now, but we're going to look at them before and after they got their behavioral therapy. So that makes our IV kind of interesting. It's time, right? First of all, this is a within groups design. It's actually a repeated measures design. It's the same people pre as post. It's before they got therapy and after they got therapy. Each level of the IV is a separate column in SPSS with their DV values for this particular type of within subjects test. So the setup of the data is different. So the DV is life satisfaction scores, they're pre and post test scores, but look at how the data are set up. So everyone here at therapy, so that first column is a constant, it doesn't actually change, but note there's a column that's their pre-life satisfaction score, and there's a column for their post-life satisfaction score. So it's kind of interesting, it is different, right? Whereas we had a column for just the IV for the independent T, here we have a separate column for each IV level, but it's got their DV scores, right? You see that? It's their life satisfaction scores pre, life satisfaction scores post, and each line's the same person. So that first person got an 18 pre, they went up to a 22. Second person got a 16 pre, they went up to 23. And that's how the data are set up. So continuing our worked example, how do you write hypotheses? How would you write behavior therapy will result in improved life satisfaction? Well, behavior therapy is time here, right? Because you got pre and post. So having had behavior therapy would mean you're post. So we think that their life satisfaction scores will be higher post. We're saying that X bar 2 is going to be greater than X bar 1. Mean life satisfaction will go up. So the pre and post, the post will be higher. Where are we wrong? Well, we're wrong if there's no change. Right? They're equal, and we're wrong if they were happier beforehand, greater than or equal to. That would be where we're wrong. So we got to disprove both of those things in order to support our alternative hypothesis. There's our means, and you can see that at the start, pre-therapy, their average life satisfaction was 19.90. After they got their life satisfaction training, it was 26. So it went up, what is that? 6.1 points. So the mean scores are indeed consistent with the hypothesis that behavior therapy resulted in improved life satisfaction, right? The post score was 26, the pre was 19. That is a higher number, but the question is, that's 6.1 point change. Is that just a couple extra red Skittles, a couple extra marshmallows in your Lucky Charms, or is that a real change? That's why we have to calculate the test. It let us know the probability that could happen just by chance, a 6.1 difference. So the Paired-Samplest t-test also has statistical assumptions that are going to look mostly familiar. So the first one is not independence, it's dependence, right? This is the test you use for a within subjects design. So the assumption is the opposite of that for independent samples T. It's that the observations in the samples are related to each other. It's a within subjects design. And it actually prints a correlational analysis as part of the output that tests this assumption. It tells you the correlation of the, in this example, the pre and post scores. And every year on the test, someone messes up and thinks that's the actual t-test. So don't make that mistake. It prints this assumption first. It's just a correlation testing the dependence assumption. So if you violate it, you can still use Paired-Samplest T, but your groups aren't actually all that related. So it actually reduces your statistical power. You might want to try independent T. So the normality is also an assumption for this test, just like it was for independent T. That is, the DV is normally distributed for both samples. That is pre and post. And you test this by looking at the skewness coefficients for each group to determine if they're approximately normal. So you want skewness less than 2 for both groups. And again, two-sample t-tests are robust to deviations from normality. They don't get that badly messed up as long as you got big sample sizes. And the sample sizes are by default equal here because you got the same people, for example, pre and post. So finally, the third assumption is, again, homogeneity of variances. That is that the DV has approximately the same variability for both samples. That is, the life satisfaction scores have about the same spread pre as they did post. That's the assumption. That's homogeneity. So again, two-sample t-tests are not robust to violations of this assumption. The type 1 error rates will be higher than your stated alpha level if this assumption is violated. So again, type 1 error inflation. And it's not tested as part of the output like it was for independent T. Why? I don't actually know. It's just not. So if you want to test it, you got to go through a different procedure to test it. So if you violate the assumption, what do? Well, there is no equal variances not assumed results on the SPSS output. It doesn't sort of print. Not only does it not print a Levine's test, it also doesn't print the alternative results you can use. So kind of your only option is to use Wilcoxon T. So what is that? That is the non-parametric equivalent of paired T. So if you look in the matrix of statistical tests, Wilcoxon T is above paired T. So on your output, when you're looking at it for the assignment this week, you want to make sure you ignore this thing, paired samples correlations. This is not the t-test. This is a test of the dependence assumption, right? So dependence are the scores pre correlate with the scores post. That's what this is. And this is not your Paired-Samplest T. So ignore this. It is a test of the dependence assumption, not the actual paired T test result. So your decision rules are exactly the same as they were for independent T. If sig's greater than 0.05, I don't care if you had a 1 or a 2 tail hypotheses, the groups don't differ. The averages of the two samples are not different. So you're not rejecting anything. If sig's less than 0.05, the samples are different. So the averages are significantly different. So if you have a two-tailed hypothesis, this is all you need. You can reject the null. However, if you got a one-tailed hypothesis, there's an additional criterion. The difference has to be in the direction you predicted. Again, right? So if you said they're going to be higher afterwards, not only does sig need to be less than 0.05, that difference needs to be in the direction you predicted. It has to be higher after therapy, for example. So again, if you have a one-tailed hypothesis, you need to divide the sig value by 2 to get a one-tailed significance, because SPSS doesn't do that for you. So here's the results. It's a little easier to read because there's only one line of results. And that very first thing, mean, -6.1, is pre minus post. So the pre-scores were lower than post. They went up 6.1 points. There's our actual sig value of 0.000. Divide that by 2, it's still 0.000. So will we reject or retain our null hypothesis? Well, we are going to reject. Why? Two things, because we had a one-tailed hypothesis. Sig divided by 2 is less than 0.05. And then secondly, the post-therapy mean life satisfaction score was higher than the pre-therapy score, right? It actually went up 6.1 points after therapy. We saw that earlier. So both criteria are true. Therapy did appear to improve life satisfaction. Finally, let's see our measure of effect size and how we write this in APA format. Our effect size is again omega squared, but squared. And it still tells you the proportion of variability. In the DV, that's accounted for by the IV, or IV's time here, remember. So the formula is a little bit different. Note that. It's still all on your output, but it is a little bit different. There's our output again from the prior slide. What do we need? Well, we need T. That goes in two places. And then we need to know our total number of pairs. That's what N is here, big N, not little n. So that's 30. You calculate that out, you get 0.69. So percentage, if you scooch the decimal over, 69% of variability in life satisfaction scores is accounted for by whether it was pre or post therapy. In APA notation, it's the same as between independent samples T. There's the general format. We just fill in stuff. A T of 29 degrees of freedom is equal to negative 8.17. P was less than 0.05. And our omega squared was 0.69. So for grandma again, what do you tell her? Well, behavior therapy resulted in improved life satisfaction with 69% of the variability in life satisfaction scores accounted for by time. That is whether they had therapy, pre or post. So that is 2 sample T's. I hope that helps, and give it a shot this week and hit me up with questions if you have any problems.